Okay, hello everyone. I just want to check does my voice is clear?
Yes, clear with you.
Okay. Hello everyone, this is Sahar. I'll be the moderator of today's webinar titled Next Generation Seismic Interpretation, presented by our instructor, Engineer Muhammad Abdelaziz. Engineer Muhammad Abdelaziz is a senior geophysicist with over 17 years of experience in geophysical exploration, seismic interpretation, and reservoir modeling across the Middle East and Africa. He has contributed to major exploration and development projects with companies such as ADNOC and SNOC and many other petroleum companies. Engineer Muhammad specializes in integrated seismic workflows, structural modeling, and reservoir characterization using different geoprediction software platforms. Before we start our session, I will make a small presentation about OBA. We will have a full live course for seismic interpretation next Saturday, presented by the same instructor of today's webinar, Engineer Muhammad Abdelaziz. You can scan the QR code to register or simply contact us through any of our social media platforms. Here in OPA, we have conducted more than 55 live courses, which are now converted into recording and available for sales. You can also scan this QR code to register in any of our recorded courses. Here in OPA, App Store is also one of our services where can access affordable alternatives for the expensive software industry. It's here to save time and money. One of our best services, which is mentorship. Mentorship is one-to-one mentoring sessions by highly, um, sorry, one-to-one mentoring session by highly experienced mentors tailored based on the needs of the mentee. Requests can include explaining the know-how of software or some of its parts, practicing on how to produce output results from software, guiding on personal data of the mentee to get the best output from it, professional guiding for PhD and master, helping undergraduate students in their project. You can visit our website opecourses.com where you can access everything from our services, whether you are enrolling in a live or recorded courses, applying for internship, mentorship, or anything else. And finally, how to be an OPE ambassador. You can either enroll in courses or take a mentorship with us. Thank you for listening. And now it's time for our session. Engineer Muhammad, the mic is yours.
Thank you, Sahar, for the introduction.
Thank you, Engineer Muhammad.
Yeah, we can start now.
Yes.
Yeah. Good afternoon, everyone. Today, actually, yeah. Today's we are gonna to bridging the seismic insight with reservoir reality through our webinar, next generation seismic interpretation integrated with structure and static model. My name is Muhammad Aziz. I'm working as a geophysicist, and I love working in the structure modeling to validate and integrate my output from seismic interpretation. In this session today, we will explore how modern seismic interpretation workflows connect directly to structure and static modeling, improving reservoir understanding and reducing uncertainties. By the end of this session, we will understand how to build a reliable structure framework from seismic data, integrate seismic attributes and inversion results into static models. Also, we will understand how to manage the depth conversion and default model challenges. At the end, I would like to invite you to see how AI and the cloud-based tools are transforming interpretation. First, let's begin by clarifying what we mean by model. The model here is a scaled-down representation for a reality. In detail, another often larger object inside it. But what is the geomodeler and what is the geomodel itself? Geomodel is a numerical version of geological concept integrating geophysical, geological observation, and the petrophysical data into a 3D grid. It serves as a bridge between geology and reservoir engineering, forming the foundation of the simulation and the production decisions. As you can see here in this figure, this is the integration from the geology data, either sequence stratigraphy, well log analysis, multi-component seismic attributes from the seismic, multi-mineral estimation from the geology, and the core analysis, all of those data integrated with the 3D grid. In today's oil and gas industry, the reasonable geological model are required as input to reservoir flow simulation program. So, but we have to remember, we only have a chance, we have one chance to develop a reservoir in corrected way, because poor modeling decisions can be very costly. The best stage for the model in the field, in the life cycle of the field, all of us know we have from the exploration to the end of the production. This is a life cycle of the oil and the gas hydrocarbon. The modeling is most valuable during field appraisal and development planning, when we have enough data to characterize the structure and the reservoir properties, but we still have flexibility to optimize drilling and the production. In exploration phase, the model, it will be conceptual, and it depends on the analog data and the conceptual models of interpretation thinking. Now, let's talk about the modeling workflow here. That's starting with the input data and the quality control for the logs and for well picks and for the input data at all. Then we are going for the geocellular grid upscaling using the seismic data and using the well logs to upscale to match the format of the modeling, in consideration the horizon from the seismic data, respect the layering relationship, depends on the surface outcrops and depends on the data itself. Then we go for the geostatistics to understand our data which correlate with the space. And then we go for the fishes modeling, that interpreted fishes modeling from the well data, and we are gonna to populate these fishes modeling into, in addition, the petrophysical parameters into the grids, inside the grid itself, and to see the propagation of porosity and permeability. Then we go for the volumetric assessment and uncertainty analysis, which is a step required for evaluation our field. Then we go for the flow simulation. In our webinar here, we are focusing until the volumetric assessment and uncertainty analysis using the input data from the seismic data in order to integrate those data with the final output of the static model. As you know, model calculations, the garbage in, garbage out. It depends on the what's the data itself. So this is the condition. It's known for us. Whatever you have a good model, but the input data is garbage, the output it will be garbage. Or if you have reliable data that the model is misfit, you will find the results also garbage. The geological data utilized in reservoir characterizations, either at 1D, 2D, 3D, static, dynamic, discrete, continuous. It depends on the kind of data, which data source you need. So this is an example for the data required for the reservoir characterizations from well surveys, location, direction surveys, depths, and this is from the simple data to the most important data from the geology and geophysics. But we will focus today on the geophysical data output and how data provides information that's relevant to geological modeling. As you can see here, this workflow from the seismic acquisition processing going for the seismic data and they try to extract the faults to build the fault framework and stratigraphic framework from the horizons. And it depends on the data quality itself. If the data quality is good, we can extract the features as well from the inversion results to calculate and to propagate the features classifications. And then we go for the petrophysical analysis to the final step of the volumetric assessment. Let's discuss about the seismic integration as well. The seismic integration here, this is our main topic in our webinar. We faced a lot of stages here, starting with the challenges in traditional seismic interpretation. Then we go for the integrated workflow. Then we will focus on the structure model. Then we will integrate with the static model and see the future trends of the AI and the machine learning, how can feed the model in integration. And then we will go for our question together. We will start with the challenges in the workflow. Let's talk about the weak points in the traditional workflow here. First, depth conversion uncertainty. When we move from time to depth, error in velocity model can miss positioning entire the structures. So it will be misunderstanding for the interpreters, and it will affect on the geological features in the model. It will be also affected in the modeling after that. The second point is the fault framework misties. In some of the cases, the misalignment between the interpreted faults and the modeled faults actually leads to unrealistic geometry. This is also one of the challenges in traditional workflow. And the third point is a limited feedback loop between interpreters and the modelers. Actually, the interpreters and the modeler often work in isolation. So in such case, the structure may be misfit, and we can find the poor reservoir connectivity and unreliable volumetrics. So we have to close this loop in order to get a better reservoir characterization. So how the solution here is simple. The solution is integration. The integrated workflow is required, actually. We have to address the depth conversion uncertainty solutions. I have some recommendation here for the solution of velocity models. So we have to incorporate well velocity data, either check shots of VSB to constrain time depth relationship by using probabilistic or stochastic depth conversion, using different model, using realization of depth models. Here in such examples, we have 3 models. In model 1, which is simple, but it is not realistic because it's considered each layer have the same velocity, which is not correct because once we go with depth, the velocity is increasing. In model 2 is come up with the continuous is good in continuous models because it's increasing with the velocity, and the V node here is considered the datum of the SRD, seismic reference datum. So it's good for continuous models. And the model 3, which is recommended for you, it's actually the V node here is considered the top of each layer. And the key here, it's a constant. It's to control the increasing of the velocity, which is a slope here. And Z minus Z node, it's telling you how deep you are within the layer. We are within each layer. So in such model, is calculating the velocity for each layer, not for the surface at all. You get my point? So actually, it's better and more realistic and flexible as well. So the second point in reducing the fault framework misties, we have to integrate fault modeling workflows. We have to align fault peaks across disciplines, the different disciplines using shared platforms like Petrel or GoCAD. Either you can go by traditional interpretation, or you can go by the AI techniques. The AI techniques here I offered for you. It's snap to seismic. Snap to seismic. This is a snap. This is a seeds to stay on the same event. So you are controlling the interpolation of the interpretation of the horizons to stay on the same event, either discontinuities in the fault plane or continuity of the horizons. And this feature, by the way, it will be, you can find it in RMS software. Fault validation through the well data, and this is one of the bridge solution to use the well trajectories and the fault cuts to check and refine fault model. I mean fault interpretations. So different ways, different techniques can help you to validate your interpretation. I would like to go again for improving the feedback between interpreters and the modeler solutions through the collaborative multidisciplinary teams. So in such way, once we close this loop, we reduce the uncertainty and enhance the geological realism. So, and this is actually the role of project manager of any projects to close this loop. In addition, the role of the company itself, it's recommended to share digital platforms like Delphi or SDUO to allow real-time collaboration and sharing and data sharing. And I have bonus tip for you. Actually, it's to run sensitivity analysis in the static model. I have some example for the sensitivity analysis here. After your interpretations, in some faults you have uncertainties. So model A, it's a 50-meter east of interpreted faults, and model B, it's a 50-meter west of interpreted fault. So then you run volumetrics, run flow simulation, and if model A gives 20% less recoverable oil, then you know you have a sensitive in the fault position. So you should refine the interpretation using more data like snap to seismic, as I mentioned, or well ties by traditional or AI techniques in order to refine this problem and match with the volumetrics. There is a software that supports this, actually modern geological problems, modern geological platforms like Petrel, RMS, Decision Space, and the T-Navigator and Eclipse. In the integrated workflow, we have to start with the seismic QC and attribute analysis. We have to go for the fault horizon interpretation like what we are using before. And see iterative and for sure it will pass through velocity and depth model integration and iterative update with the geomodeler static model population. Here in such examples, I'm focusing here in the role of seismic attributes and how it's gonna be fit to show the tracking of the salt dome here. And the blue figure, actually, we are using the correlation of the tracking of the horizons using the traditional techniques and using the AI interpolation techniques. In the correlation here, you will find the color bar is respective for the accuracy of the picking of the horizons. Actually, we are first with the seismic QC and attribute analysis. Then we move to fault and horizon interpolation using both manual and AI assistant tools. Next, we develop a velocity model constrained by check shots and well data for accurate depth conversion. And this is the traditional workflow. And the structural models, the structure framework at the end, it will be extracted from faults and horizon, is then used to build a sealed 3D grid. The structure framework building actually more focusing on the faults. So if you are using a traditional seismic interpretation, it's recommended to use the vertical seismic sections and depth slice as well, or time slice, depend on your data as well, to see the trend of the fault along the depth slice or for different depths or different time. So, and also you have to prepare a geological consistent grid for geomodeling. And also, if you can import a framework into geomodeling software like Petrel or GoCAD, it will be better. And iterate between seismic interpretation and geomodeler refinement. Then you can validate your production data and the additional seismic insights. In the static model population, try to populate a structural model with petrophysical and geological properties and use seismic inversion, well logs, and the core data for facies, porosity, saturation, distribution. And you can prepare a model for dynamic simulation or reservoir engineering, because the static model here, it will be an input data for flow simulation. The key benefit here of this workflow is integration between geophysics and geology, and reduce the uncertainty through the iterative updates from time to time to close the loop between the interpreters and geomodeler. Here also, I would like just to focus on the integration between the grid making from seismic interpretation, because internal layering based on the conceptual modeling. And also, if you have a good seismic data, it will help you to know the layering. In such outcrops, you will find this is the proportional layer here is proportional to each other. So you will use in layering model this one. And once you go, if you have this technique, if you have this feature here, like pinching out of the strata with alluvial channels, this is from the surface outcrops. And if you have this from the seismic data, it will validate the layering proportional distribution, and then we can use the parallel to top layering this one. All of this workflow we can discuss more details in our course step by step to reach to the final static model. The structural modeling focusing, actually, I'm focusing here on the fault uncertainty handling with different scenarios, depth conversion as well, approaches, and sealed fault framework. The fault uncertainty handling scenario, actually, we have problems and solution. We have a problem because the fault position and the geometries often uncertain due to seismic resolution limits. This is the first problem. The second problem is the ambiguity in the fault connectivity, especially in complex fault system. Single deterministic fault model may not capture the subsurface variability. So in the solution here, we are build multiple fault scenarios. Fault scenario, low, mid, high displacement, alternative geometries, and even we can use probabilistic for fault modeling or stochastic fault simulations. Incorporate all this uncertainty together around the key faults, around the major faults, and validate with well data and the fault cut points, And then if you have a chance to use the machine learning new techniques like regression, RGT, or reinforcement learning, so it will be helpful for you to validate your fault interpretation. Here, in some structural models, we have is such problems. As you can see, this is uncertainty and challenges and solutions. I have faced these problems. I would like to share with you. This through the fault extrapolation distance does not give the right results, because here is the 50 meter actually, and here is the 500 meters. So it depends on the drag itself, and depends on the data extracted from the interpreter itself. So you have to correct it in the model, and this is the benefit of the structural model here. In addition, also some extrapolation happened, depends on the anomaly from the model horizon in the corner point grid. We can also manual adjust the horizon by changing the horizon fault lines, and this is one of the solution inside the software. Also, you can handle by manual editing these problems. I'd like just to share with you the challenges and solution also by handling the interpretation of the faults through anti-track, which is one of the machine learning methods in Bitrel software. This by focusing on structural geology rather than conventional segment picking. There is 4 independent steps for the anti-tracking. You are using the data, you understand your data very well. So you have to enhance the special discontinuities in your seismic data using the edge detection algorithm, like variance chows edge detection, as optional for preconditioning your seismic data by reducing noise. Try to go for anti-tracking directly. It depends on data, and try also using this enhancement of the discontinuities and see the effect. Try to generate the anti-track cube, as you can see here, and then extract the fault patches. And once you extract the fault patches, it's a lot of patches here. This is automation extraction, so you have to filter, you have to modify, and then you create the fault interpretation models. So in the patching extraction here, you have to QC very well, and this is the rule of experience now using the machine learning, but it's not depending the data output directly, because you have to use your experience, your geological background to validate the output. In depth conversion, also there is a challenge and solution. The velocity model also can destroy fault geometry in depth. Error in depth conversion can lead to unsealed faults or unrealistic fault throw. Misalignments between faulted horizon and the wells in depth domain. Sorry for that. Just let me just a second. Sorry, my son was crying. So let's continue here for the challenges and the solution for depth conversion. The solution here, we have to apply average velocity along all the surfaces, and check whether average velocity varies linearly between the horizons. And then you are going for interpolation between the horizons, and you are using the amplitude, the volume, and depth using different velocity models to check with different velocity model. For example, velocity model 1, velocity model 2, until you calibrate the depth conversion matching with your well data and the peaks of your data. It's not necessary to capture exactly at the well tops. The error shift is okay, is acceptable, unless if it is common for all the peaks. And also you can run sensitivity analysis, as I mentioned before, that will be impact on the fault ceiling after that. Also in the fault ceiling analysis, one of the challenges here, and we have to have the solution for it. The seal default framework may look correct geometrically, but violate geological rules. Yeah, this is actually issues like horizon truncation, fault juxtaposition errors, or hanging wall mismatch, fault throw sense inconsistent with the stratigraphy original context. So this is the problems we faced in our interpretation. So we have to perform fault juxtaposition analysis. Either you go for the simple Allen diagrams, through versus depth plots, or you can go through fault scene analysis in the petrel, but you have to make a model and populate the fishes, especially the V shale, in order to adjust the fault juxtaposition and run horizon truncation checks against the fault planes, and to compare with the regional stress regime and analog data, just to confirm the juxtaposition and the throw it's as well. Some of the times there is a QC automation tools in some softwares to flag geometries and geological inconsistencies. So it depends on the available software you have, available platform you have. Once you have one of these solutions, you can validate your work. So this is actually involve the geophysicist with the geologist in building and validation sealed frameworks through multidisciplinary collaboration, key to balancing data fidelity with geological reality. So in these examples, as you can see, actually, this is one of the exercise I did for the fault seal analysis in petrel. So as you can see here in the left-hand side, you have V-shield distribution in the reservoir model and you have the yellow areas sand juxtaposition, while the brown indicates sand against shale or shale against shale. So this is a good exercise actually for knowing the juxtaposition and the smearing along the fault plane itself. Integration with the static model. As I mentioned, we are focusing on the data and the seismic data here. So data flow from seismic into static model. Structure grids, actually it's considered feeding fishes in the property models. Fault framework controlling fluid flow, and the feedback loop for consistency. Actually, if you focus with me, I repeated this the feedback loop many times because this is this is integration secrets for successful modeling grid, especially in the static model. Data flow seismic to static model. As I mentioned, the structure grids feeding fishes and probability modeling, because once you have the fault modeling, so you have the structure framework, and if you go for the pillar grading or the grids using the cell dimensions in respect with the requirement of the engineering, so structure framework plus continuous data porosity permeability plus discrete data fishes and net to gross, you can find the foundation for population for fishes model, either depositional environment or lithofishes, and petrophysical models for porosity permeability with water saturation, or whatever you need to propagate from the petrophysical data. So grading, this grading ensures geological consistency and spatial resolution. So this is as I mentioned, the feeding now from the seismic to the static model. The fault framework controlling fluid flow. As we discussed, the seal fault framework define flow barriers and compartmentalization. So the fault transmissibility models influence pressure behavior, hydrocarbon migration, and it's considered a crucial for reservoir simulation and development planning. So as you can see here, this link and this propagation of the of the of the facies along the fault planes, showing the controlled of the fluid flow, and showing the flow barriers itself, and the compartmentalization is valid through these faults. The feedback loop for consistency, static model compared with the seismic well production data, all of these together actually to avoid the depth mismatch or to avoid the unrealistic fishes. The trigger iterative updates is required so you have to revisit seismic interpretation during this loop. You have to refine velocity models. You have to update grid and property models. So, in some steps, you have to come back to validate, and then you go forward for another steps. So once you promote a closed loop workflow across disciplines, geology, geophysics, reservoir engineers, the message it will be simple. Static model is only as good as the seismic and structure inputs. The solution in integration. Let's go for the future trends here. I'm discussing with you here the new approaches in seismic interpretation through machine learning and AI, and also the structure uncertainty, and using cloud-based collaboration platforms in order for integration and facilitate the interpretation. And once you are faster with the static model, it will be a good input for the dynamic model. So the fast integration between static and dynamic models, it will also reflect on the in the good model. So the innovation now is crucial because we have a huge data, and we have on our local workstations. In addition, we have a fewer geoscientists. So the cloud computation now it's a challenge. We need this actually for minimize this huge time spending through interpretations. And let's think together in the new approach, not spending so much time in picking. However, there is now the machine learning seismic interpretation techniques is applicable in order to think more and more in the technical aspects. So as you can see now, the energy transition now is happening because once the required for CCS now became so much important. So we have to think in other resources in order to validate our experience. So the machine learning now, we have to have an idea about these techniques and this methodology. This machine learning is a type of artificial intelligence that allows a computer program to learn without being programmed. So this is I captured some examples from the machine learning methodology and analytical methods, either unsupervised learning, supervised learning, or reinforcement learning. So once we go for the definition in seismic interpretations, we will start with artificial intelligence, which is a technique enable machines to mimic human behavior, to minimize the human behavior errors. Machine learning, it's a subset of AI techniques which use statistical methods to enable machines to improve with experience. And finally, the deep learning here, it's a subset of machine learning which make the computation of multi-layer neural network visible. And this is the technique now we are using recently from the 2021 through some methodology. I'll speak about it in the next slides. The thinking from 2017 for different analytical techniques like slope based, This is the name of the paper by self, and this is so I'm capturing some snapshots from the paper from 2017 slope analytical methods, which was based on seismic local reflection slope, but actually it's fail in tracking the horizon in area of discontinuities. As you can see, this is a seismic line fault, and once they run the slope based techniques, they capture all the noise. Okay, but once they go for the tracking the horizon, it's failed in the tracking the continuous, especially in the area of discontinuities. Then some of the people thinking on 2017 analytical method based on seismic waveform along the faults, but also fail in tracking the horizons in areas of discontinuities as well. And then they are gonna to use the relative geological time, RGT. But here, this is a layering interpretation, not volume, okay? But still, actually, they are fail in capturing structure among the interpreted horizons itself. Okay, they succeed to interpret the horizon like that automatically, but they fail in capturing the structure between these layers. In 2019, the binary classification, also one of the analytical methods, using a deep convolution neural network, try to extract here. Here you can extract the data from the horizon data from the seismic interpretation. And there is also some of the techniques called the hybrid methods. This is automatic tracking for seismic horizon using feature analysis and optimization algorithm. And there is also segmentation methods, which is analytical methods using this one, extracting horizon surface from the 3D cube using a deep learning, as you can see. And finally, the regression, which is deep relative geological time in 2021 for interpreting horizon and faults simultaneously. But this is for the volume to volume neural network. So, and they achieved a good approach in that. As you can see here, this is input data, and they achieved the RGT estimation for the horizon and fault detections, and then extract the horizon and the faults from the seismic interpretation as well. As you can see, this is continuous geomodel and capturing strata slicing through isogeological times. And they did some experience, some approach here to use the automatic plus human intelligence. And the percentage, as you can see here, is a 10% of geoscientists help with this automation interpolation for the faults and the horizon as well to solve the complex fault model. The new cloud environments such as OSDU, actually, it's a crucial component in the future success of AI. They are now training many techniques in order to make a great interpretation from the operators itself. The future trends, actually, as I mentioned, faster integration with the dynamic model. It will be the seismic interpretation is a foundation step for reservoir characterization, requiring time to reach quality required for the rest of the workflow. So you can imagine here, this is our workflow, and this is the AI workflow time. So reduce time cycle and increase efficiency, but should be with our experience. The last slide here in our webinar, I would like just to return to our experience to make you save. We are still having our job because they are still dream in machine learning model for the idle structure model because they have some problems. Faults are continuous with no missing bits. They are dreaming to achieve that. They are dreaming to achieve to impact the fluid flow consistent. They are dreaming to connect it with the faulty network and validate the compartmentalization with automatic and with dynamic data, fluid pressure and production. And here's some examples: fault probability, fault extraction, fault network. But it should be come back to our interpretation, our experience to analyze, filter, and edit. And this is depth migration seismic line. In addition, acoustic impedance prediction by DNN. Especially another machine learning prediction here for stratigraphic fishes they are doing, but still it's not fit 100%. Um, to wrap up our webinar here, this is a comprehensive 20-step workflow designed for professional interpreters and consistent with modern integrated practice used in Petrel Kingdom or decision space as well, and similar platform from seismic data preparation to integrated structure and static modeling. So this one classified into phase one data preparation and quality control, um, phase two structure framework interpretation, phase three depth conversion and structure modeling, and phase four advanced interpretation and integration using AI techniques, especially for advanced project. Thank you. And any question for you? Any questions so far? I would like just to thank you for your time and for your attending our webinar. Thank you, Sah.
Thank you, Engineer Muhammad, for this great session. Thank you for your effort. Now the time to receive attendees' questions.
Yeah.
And we have 2 minutes break to fill the feedback form. I will put it in the chat box, okay?
Okay.
Please, if you have any question, write it in the chat box, please.
Thank you, Muhammad.
Any questions? Please don't forget to fill the feedback form. About certificate, it will be generated automatically on the website. It will be tomorrow, inshallah.
There is a question here, actually, from Mr. Muhammad Al-Aidi, how we could integrate it with geomechanics. Actually, once we integrate all the data together from the seismic interpretation to fault modeling, better grading, and populate our fishes, especially for porosity and permeability, then we can go for the measuring the stress and the strain all over the fault planes. So it depends on the well data we have to capture the to go for the geomechanics analysis to capture where is exactly the stress, the major stress and minor stress in which directions for using it in frac. I mean hydraulic frac if we are gonna to test our reservoir. So it comes after after population, Mr. Muhammad. I hope my message delivered well for you.
Thank you, Engineer Muhammad, and thanks for your time. And see you soon in upcoming course, inshallah.
Inshallah. Thank you all. Thank you for this.
Thank you. Thank you for attending this session. Thank you.
Thank you.